Welcome back to another video at the channel, and today I am very excited to share to you the 2022 BMO Round 1 solutions. So BMO Round 1 is a British Maths Olympiad contest which took place in 16th and 17th of November 2022, which is very recent to the time we published this video. So it is a contest of 3.5 hours, consisted of 6 problems, and around 1,600 students take it each year. 100 advance to round 2, and then more will be selected to participate in the IMO, which is a 6-person team representing each country. So today the video will be only about problem 1, 2, and 3. A part 2 video will be on problem 4, problem 5, problem 6, because if I put all 6 problems at once, it would be too much for you to consume. So without further ado, let's get started with problem 1. A road has houses numbered from 1 to n, where n is a 3-digit number. Exactly one of the k of the numbers start with a digit 2, where k is a positive integer. Find the possible values of n. So basically, the first problem is always more straightforward than the rest, which is basically how Olympiad works. So we can start off by first let m be the number of numbers starting with the digit 2, then m over n will be equals to 1 over k. So this implies m needs to divide n, and m times k equals to n. So we can divide into basic cases, such as when 100 is smaller than n equals smaller than 199. So notice there are m equals to 11 because of number 2, number 20, 21, and all the way up to 29. Therefore n must be a multiple of 11. So because n has to divide n. So we have n equals to 110, 132, 121, I left it out there. 143, 154, 165, 176, 187, and 198. If it fulfills the requirement, and it is in fact in the range 100 smaller equals to n smaller equals to 199. So the second case is 299 smaller or equals to n smaller to 1000, because n must be a 3-digit number. So notice m is actually equals to 111 because of 2, 20 all the way to 29. And then we have 200, 201, 202, and so on to 299, which are 100 numbers. So adding them together, we would have m equals to 111. And no matter how much you increase n, let's say 300, like 301, and there's 402, 506, etc., there will always be only 111 numbers starting with digit 2. So we have n must be a multiple of m, so we have n equals to 333, 444, and so on to 999. So the third case would be a bit tricky, and we would have 200 smaller equals to n smaller to 299. So notice here n is equals to 188 plus m. So we have m divides n is equivalent to m divides 188 plus m. So this implies m must divide 188. And we would use simple case bash. Let's say use simple case bash, and we'll have m equals to 47 and 94. Okay, so notice 12 is smaller equals to m smaller equals to 110. Therefore, if we plug it back in, we'll have n equals to 235 and 282. So summing up, we have n equals to 110, 132, 143, 121. I left out here by mistake. All the way up to 198, 235, 282, 2 special cases, and 333, 444, all the way up to 999. And that is the first problem of the BMO Round 1 2022. So let's move on. So second problem. A sequence of positive integers a_m begins with a1 equals to a and a2 equals to b for positive integers a and b. Subsequent terms in the sequence satisfy the following 2 rows for all positive integers n. a2n plus 1 equals to a2n times a2n minus 1, a2n plus 2 equals to a2n plus 1 plus 4. Exactly n of the numbers a1, a2, all the way up to a2022 are square numbers. What is the maximum possible value of m? Note that m depends on a and b, So the maximum is over all possible choices of A and B. Okay, so it is quite an interesting sequence problem and mixed with number 3 and a bit of algebra. So let's get started. So observe that a2n plus 2 is equal to a2n plus 1 plus 4. And here I wanted to substitute a2n plus 1. And we would have a2n times a2n minus 1 plus 4. And we can substitute again a2n equals to a2n minus 1 plus 4 times a2n minus 1 plus 4. And if expanded, you will have a2n minus 1 squared plus 4 times a2n minus 1 plus 4. And we will have a2n minus 1 plus 2 squared, which is very interesting. So that means for any a2n plus 2 and larger equals to 2, it must be a square number. And so it can prove half of the problem. So if we look further into the next few terms, and we have a2n plus 1 equals to a2n times a2n minus 1. So a2n plus 1 is a perfect square for n larger equals to 2 if, so IFF means if and only if, a2n plus 1 is a perfect square. So inductively, we require a5 to be a perfect square. So let aq squared equals to a5 equals to ab times ab plus 4 equals to ab squared plus 4ab. So for the purpose of simplifications, let a equals to u, and we have u squared plus 4u minus m squared equals to 0. And using the quadratic formula, we will solve for u, and we will have u equals to negative 2 plus the square root of 2 squared plus 4. And the negative answer here is rejected because ab is a positive integer. So u must be larger than 0. So we also know that u must be an integer. So because ab is a positive integer, so we have q squared plus 4 must be equal to a perfect square. So let q squared plus 4 equals to v squared for some positive integer v larger to 2. Therefore, we would have v minus q times v plus q equals to 4 using the different sets of squares, and we will have v minus q equals to 1, v plus q equals to 4, or v minus q equals to v plus q equals to 2. And solving them, we will actually find out no positive integer solutions for v and q. So that means there are no solutions such that a2n plus 1 can be a perfect square for n larger or equals to 2. So now we can consider a1, a2, a3, and a4 because we want to maximize m. So consider a3 equals to ab and a4 equals to ab plus 4. And below we've proved that AB and AB plus 4 cannot both be perfect squares. So proof by contradictions. Let AB equals to x squared, AB plus 4 equals to y squared for some positive integers x and y. So we will have y squared equals to x squared plus 4. And on the previous slide, we can already show that uv, which is here, y and x has no positive integer solutions. So they cannot, a3 and a4 cannot both be perfect squares at the same time. So in order to maximize m, we could have a and b to be perfect squares. So a3 can be perfect squares. So a1, a2, a3, a6, a8, all the way up to a2022 are perfect squares. So the maximum value of m is 1012. So let's move on to the third problem. So problem 3 is a geometry. So in an acute non-isosceles triangle ABC, the midpoints of AC and AB are B1 and C1 respectively. A point D lies on BC with C between B and D. The point F is such that angle AFC is a right angle and angle DCF equals to angle FCA. The point G is such that angle AGB is a right angle and angle CBG equals to angle GBA. Prove that B1, C1, F, and G are collinear. So normally in Olympiad contest, they won't show you the diagram. So you will have to draw one yourself with compasses and a ruler. Not a protractor. Remember, you cannot use protractor in Olympiad contest. So if you don't know how to sketch diagrams, I suggest you to learn it quickly because it is very important in Olympiad contest. So below is a sketch of diagram. I drew with GeoGebra, but in contest you obviously won't have GeoGebra. So here, so we know that AGB is a right angle, AFC is a right angle, and GB is the angle bisector of ABC, FC is the angle bisector of ACD. So let's move on. And since AFC is a right angled triangle, by angles in a semicircle, a very basic mid-high school geometry theorem, we would have B1 will be the circumcenter of AFC. So that means AB1 equals to B1F equals to B1C. And AC is the diameter of a circumcircle of AFC. And similarly, you can prove that C1 is the circumcenter of triangle AGB, and AC1 equals to C1G equals to C1B, and AC1B is the diameter of the circumcircle of AGB. So this implies FB1 is equals to CB1, and it implies angle B1FC equals to angle B1CF. And we know that FC is the angle bisector of angle ACD. So we have angle B1CF, of course, equals to angle ACF equals to angle FCD. So that means BFB1 is parallel to CD, which is also parallel to BC. So very similarly, we can prove that GC1 is parallel to BC. So in order for B1, C1, G, and F to be collinear, we have to prove B1, C1 is parallel to BC, parallel to GC1, parallel to FB1. Okay, so note that AC1 is actually equals to C1B and AB1 equals to BC, because they are the midpoints of AC and AB respectively. So B1, C1 is therefore the midpoint line of triangle ABC, or you can understand this as triangle AC1B similar to triangle ABC. So therefore, C1, B1 will be parallel to BC due to the properties of similar triangles. So AB1, C1 equals to ACB, and you have a pair of parallel lines. So that basically concludes our proof. So B1, C1 would be parallel to GC1, parallel to B1F, parallel to BC. So this means B1, C1, F, and G are collinear. So this wraps up the part 1 of the BMO Round 1 solutions. Round 2 will be, part 2 will be coming out soon, explaining question 4, problem 5, and problem 6, which would be more complicated. So I hope you enjoyed and understand the video, and don't forget to subscribe, like the video, leave a comment, or share it around to others so they can see the BMO Round 1 solutions. So stay tuned for part 2. Thank you very much. See you guys.